Okay, let's begin. We have not that long left. So we are talking about OpenMP now. And what I was saying is that I am going to give you just high-level design and just stuff to get you started with OpenMP, but don't expect to learn entire OpenMP in class. Everything that you're going to even need for this assignment is not necessarily going to be in the class, okay? But enough to for you to figure out how to figure out the rest of it. And the design of OpenMP is extremely simple and powerful, actually, in terms of how you parallelize code. Right? So if you have done, for example, thread programming, you probably, here you won't get 6 so soon. Okay? Here is an example of how you would do OpenMP based parallel programming. This is compiler supported. Okay? So you put in your code instructions for the compiler for it to be able to parallelize. And the main way, or one way in which you give instructions to compiler, are these hash pragma instructions. Okay? And all OpenMP pragmas begin with hash pragma OMP. And then there are lots of different types of OMP instructions, OMP guidance that you give to the compiler. Okay? Here is one simple one. It says pragma OMP parallel, and then there is an open brace and close brace, which says that region is to be run in parallel. And then you write some code. Okay? It may be a function call. It may be add some variable to some other variable, whatever is your heart's desire.
All the variables are available.
We'll talk in more detail. Yes, they are all available, but there are features that we need to understand. It's also hidden here. It's not very explicit in this struct how many different times you want to run this common thing. Okay, that is driven typically by environment variable. You can also control it explicitly. For example, in this parallel call, you can say pragma OMP parallel 10. So that means you run this 10 times. 10 parallel sessions. Okay, everybody is running concurrently. If you have 10 CPUs, they're running exactly at the same time. If you don't have 10 CPUs, then there are 10 threads internally which are going to context switch with each other. Okay, and so the notion of threads still is valid. So in principle, you are saying that I want 10 threads. Each thread should run this piece of code. Okay. When I haven't said anything, there is some default that's getting used. And most compilers' default is the number of cores. So if I run it on my laptop, it's a dual core CPU. So it's going to generate 2 threads.
That's something decided at the compile time, right? Not at the runtime.
There is a dynamic version also. You can create these also at runtime. Okay. But in this case, the number of threads, because it's not being specified here, is predetermined.
Sir, this dual core machine CPUs, per core we can run 2 threads concurrently.
Using hyperthreading? Yeah, so if you know you have hyperthreading, you can say, don't run just 2 threads, run 4. Okay. Right? But and in fact, if you have turned hyperthreading on, when in response to your instructions, compiler is executing some library functions, right? It has its own code. And it's going to query the system, asking how many cores you have. If you're running hyperthreading with a dual core machine, then it will get the answer you have 4. Okay? And so it will think that you have 4 cores, and so it will run 4. And so inside, you may do something like switch a variable, a function call that you make, which tells you you're one of so many threads. So it says my thread ID is 0, your thread ID is 1, the third thread's thread ID is 3. And so depending on your thread ID, you can do different things if you want.
So, parallel directive does not tell you to parallelize the code, it tells you to run it n times.
Exactly. It is not a piece of code that for which parallelism is to be figured out by the compiler. It is a piece of code that the compiler has to generate n threads to replicate the execution of. Okay. And now you've got certainly some n number of threads running this piece of code, right? You've got to figure out how their variables values get reflected with each other and all that. We'll talk about it. Once they are done with their executions, we are going to come to the end of the construct. And once all of them have reached the end of that construct or end of their pieces of code, one thread will continue on from there. Okay, so there is an implicit barrier which is at the end of that code, at which all of the threads come and stop, and after all have reached there, they join into a single thread. So it's a fork join model. Okay. So in OpenGL terminology, there will be a master thread that is going to reach. So there is execution before, right? This is some piece of code somewhere in your program, and the execution has reached this point. Whoever was executing here might have been one and the only one, or might have been one of many already, because there's some other parallel construct that forked off many. Okay, that who reached there is called the master thread, and it's going to generate n-1 new threads, which all will die at the end of the barrier when they join, and the master thread will continue on.
There are originally 3 or 4 threads running, then each would create 10 threads.
So each thread may or may not reach this OMP pragma. Right? They have their piece of code, and for some condition there may be a jump. For some condition you reach this.
If all of them
reach there, then everybody will replicate 10 times. Right? Sorry?
We can nest these OMP.
Nesting is allowed. It's actually turned off by default because it was buggy in the beginning, and also people had trouble wrapping their mind around how to nest parallelism. But it's not buggy anymore, at least. People still may have problem wrapping their minds around it. You can turn it on. You can nest it. Okay. Sorry? Nesting means you may have one OMP parallel construct inside another bigger OMP parallel construct.
So in that case, how does some threads will wait until you have context switching in that?
No, so there is context switching. So because we don't know how many processors there are, we don't know how many threads we are going to run, right? So context switching is implicit, and then there is this thread mechanism that the OS understands, implements, supports, and so context switching is allowed among threads. Okay, and so when you start your program, main first instruction says OMP pragma, pragma OMP parallel, and 2 threads get forked off, and each in its execution encounters another OMP pragma parallel, right? So each will fork off another. So now I've got 4. I may or may not have them 4 at the same time, because this may be running at its own pace. This may be running at its own pace. This may not have reached the pragma yet, and this guy may have reached the end of the pragma. Okay, so there is no notion or understanding that these are running at the same speed. But yes, it is possible that at any given time 4 threads may be running. It is possible that only 2 threads are running, because this guy forks and this guy, or 3. Right? You forked into 2. This guy forked and this guy hasn't forked yet. This guy even joined, and this guy now forks.
So OMP pragma is equivalent to the fork command in C, pretty much.
It has much more baggage than fork. Okay. The sharing is either implicitly determined or explicitly provided, but you have essentially a set of variables that are shared, meaning that they are shared across this group that is created at the parallel construct, meaning that anybody who writes to that variable is communicating with other threads in that group what the value of that variable is.
So it also, the sharing also goes along with the nesting thing.
Right.
It goes well with the nesting.
Right. So what it says that, so not talking about all the different types of variable yet. Suppose I've got a shared variable. This code doesn't have much. Say n was a shared variable. Okay. Inside this case 0, case 1, etc. When I say n equal to 3, I'm talking about the exact same memory address that some other thread is talking about. Okay, that's all it means. The mapping of the name to the address that is controlled by user either explicitly or implicitly.
Two threads are running simultaneously, they may be accessing the same variable at the same time. Won't there be any confusion?
There will be confusion. Yes, it's your job to fix that confusion. But when you are sharing, then yes, you have to somehow figure out how to make those updates be consistent with each other. And we'll very quickly talk about what memory consistency model is assumed by MPI, OpenMP, which means that every implementation of OpenMP. So OpenMP is not a software, right? It is something that is going to be built into a compiler. OpenMP doesn't, you don't get a library called OpenMP, just like you might get for a thread, POSIX thread or Windows thread. So different implementations of OpenMP may have slightly different properties. But OpenMP says that these are the things that are undefined and these are the things that have to be guaranteed. So there are some consistency rules on memory that will have to be guaranteed by all implementations of OpenMP.
So OpenMP is just a model.
It's just a model. It's a specification.
And what are the implementation?
GCC implements it. Visual Studio implements it.
The typical compiler.
All compilers implement it, right? They may be at different versions. So the latest version of OpenMP right now is 3.0. GCC 4.3 or so implemented 3.0 came out in 2008. Visual Studio is at, I think, 2.0. There was also a 2.5. So GCC 4.1 will be at 2.5 or 4.2 will be at 2.5. And similarly, Intel's compilers, Intel actually implements 3. Intel's compilers will give you also 3.0. Latest compilers. Okay, so here is the execution model. Some thread is running through its code, okay, and it's going to encounter this pragma from the source code point of view. And at that point, either through the pragma instruction or through some other library function that you may have called earlier, or through an environment variable you may have set earlier, or through the default that OpenMP sets, some number will be known that so many threads need to be created. And that number minus 1 threads will be created because one of them is the master thread who encountered this. They'll all run their version, they'll all get their own PCs, right? This is honest to goodness OS thread. And they will run this code, piece of code. And at the end of the piece of code, they'll wait for everybody else to get to that same piece of code. Okay. Once everybody gets there, the master will proceed. And at that point, there is no trace of n-1 threads. Okay.
In that said like whatever can be done with POSIX threads or any thread implementation.
Because this is built upon POSIX threads or Windows thread or some other thread. So the compiler is actually assuming that there is a thread implementation. Okay. And when you, for convenience, when you build your code, compilers have a quick flag to say enable OpenMP. Okay. For example, if you say GCC, you simply say -f OpenMP. If you use Visual Studio, then there is a pull down thing that says enable OpenMP. Okay. Internally, when you say -f OpenMP, it is saying -l thread, pthread. Okay. And so it's expanding to all those things. It's expecting that all those things are needed. It provides -I include paths. It provides load paths wherever you may have installed the stuff at the compilation time of the compiler. But you simply hide all of that behind an -f OpenMP, and all those internal mechanisms for threading, thread creation, thread fork and join is going to be called by the compiler for you. All right. The memory model, probably if I'm going to start, then it's going to take me 10 minutes to explain it. So might as well stop here because it's 6:30. We will continue with the memory model on Saturday, because there is a class on Saturday, and hopefully finish as much of OpenMP as we are going to talk about on Saturday. Okay. Any questions? Locking is on top of the model. Right? Memory model says when two people share, what does the underlying implementation of OpenMP provide? What must it support? Okay, and we talked about basic notion of consistency, right? If there is a variable that says 5, somebody must have written it. That's basic expectation, right? It shouldn't be 5 that just appeared there from nowhere. Okay, so we'll talk about that in more detail. We will actually talk about memory consistency models in a more broader sense later on in the course. But we'll talk about what it means for OpenMP. There are a couple of things I wanted to add or revise from the NVIDIA architecture discussion that we were having. One is that I had copy pasted from the GAT architecture to Fermi architecture. That one had 128 kilobytes of L2, which was not getting used. But by the time it went to, and between GAT and Fermi, it had gone up a couple of times also. But by Fermi, it had become 768 kilobytes, which is the current size. The other discussion we had about the size, the number of threads that can be run. And that limit is 48 times 32. So there is something called a warp, which is the SIMD width. Right? 32 threads have one instruction, right? Another 32 may have another instruction. And so there are 48 of these that can run or be live inside one SM at any given time, which means 1500 something, 1536 or so. Threads whose context can be maintained together. Okay. There may be reasons why you cannot run all 1500 of them, because either they use too much memory, more memory together than you have, or the register usage is high, or so on and so forth. But in principle, you can run that many threads together.
So shouldn't these be equal to the number of cores? Or is it because it is...
No, number of cores is only 16 on a single SM.
As in the SMs into number of SPs.
Number of SPs is 16, okay, in one SM. There are 32 of them.
32 SMs.
Right?
Each is having like 3 context switch. So
No, no, no. Within one SM, you can have 48 SIMD groups, right? One SIMD group is 32 threads, and you can have 48 of them live.
So, but in one SM there are only 16.
16 processors, 16 execution units, but they actually run 32 because you do 2 every clock, right? So effectively, you can think of it as having 32 execution units, although that's not physically true, but logically you can think of it that way. And so 32 threads will run in a given clock, one instruction, okay, on one SM. But 47 other groups of 32 threads may be waiting to run their instructions while this guy is running one instruction. All right, so 48 such live groups may be there at any given time. Okay, that's the maximum. All right, so let's come back to so this discussion we just had.
Sum up to 500 something, 500.
12.
12.
Yeah, 512 total cores. There are 16 SMs. So if you look at this slide, this showed you the SMs arranged, right? So each a pair of green columns forms one SM. And they're 8 at the top and 8 at the bottom. All right, so getting back to OpenMP.
So there is a lot of variability in the architecture of various different GPUs, right? So does that mean
Very little variability. And there are some details that are different, but the overall high-level organization, that's not changing.
so? I mean, are compilers intelligent enough to adapt code to these different?
We'll talk a little bit more about it when you start to program those things. But in compiler, you actually can provide the output. It's a cross compiler, so it can compile to all these different architectures. Right? There is this intermediate language which is sitting above the assembly language and below the high level language called PTX. Okay, and the idea is that it will compile to PTX, which then will subsequently compile to the actual instruction set if that changes, which it does from Tesla to Fermi.
What I wanted to know was, to make the best use of the thing, how much does the user program need to change?
If the user takes that into account, it can do a much better job of it than the compiler will. Okay, and the truth is that the CUDA programming model exposes to the user all those details, right? It says how many SIMD-wide things do you want to run, right? Of course, you can say more than 32, but then it's going to break it down into chunks of 32. Okay, so once you, and similarly there are other details, how memory is accessed and so on. If you organize that your memory accesses are efficient on a given architecture, then you will be better off. It is on that architecture, right? It is possible to one thing that I said earlier, I should repeat. It's not that different NVIDIA's GPU architectures, even they are changing, are that starkly different, right? So similar optimizations will work on most of them. It is possible to do the same thing that you would be doing by having compiler interpret and do it, right? And there is research ongoing on getting the compiler to do better and better at it. Right now, the state of the art isn't there that the compiler can do better than the human, and I suspect it's never going to be there. But at some point, it's going to be good enough, and then you start using it. Okay, now back to the OpenMP programming model. We had talked about the execution model, which said that there is a notion of threads, and at any instant you can say run so many threads in parallel. Okay. We also need to understand what the model in terms of the shared memory is and what kind of consistency is going to get provided. Very explicitly in the specification of the design, it is given that different processors may have local cache. Right? They may be sharing memory and somehow talking to the memory through a bus, through whatever interconnect, through whatever sequence of switches or other processors. And so it is understood that sometimes memory access may be slow and some things will have to be cached. And so there is this notion that a processor has a local view of the memory. The same variable, it may be sitting in cache with value equal to 39, but in the main memory, its value is something else. Okay, and so the consistency model accounts for this, that there may be different variants of that memory location, and that's why it's a very weak consistency model. When we, as I had said, that we'll discuss at a theoretical level what consistency models mean, we'll realize that this is in that spectrum of weak to strong consistency model among or weaker than what is officially called the weak consistency model. Okay, so we can call it the weaker consistency model. There is a notion of private memory, meaning that I generate a thread and thread shared memory, but there may be some thing that sits in the main memory, but is only visible to this thread. Okay, so it's private to this thread. So you can create thread private variables, and there are these shared variables, which means that others have access to it, but doesn't mean it's in a consistent state at any given time. There are features to make it consistent if you want to, but it's possible that different people are seeing different values of that variable because they have it locally cached. All right. So the tying up of shared and the temporary view means that whenever a parallel region gets created, right, which says that now I'm going to start fork 5 threads, each one will get a local address to do local work on that shared variable. And at some point, they are going to make consistent those local copies. Okay. In some sense, this is also true about private. Only thing is, in private, there is no notion that they're ever going to make consistent, unless at the end of the parallel construct you say that I want these private copies to be collated in a certain fashion. But there is clear notion that there are n copies of that variable, and you have to specify what to do with n different values. Okay. Go ahead. You go ahead.
So here we are having like one part of the program is parallel. We have a program which we
There's some region
is
running in parallel.
Is it possible using OpenMP to have the entire process itself be parallel? For example, I may have I would like to have small processes which read data using some I/O or something like that.
You can still do it with thread, but you will get a single process. Okay, so they are going to be sharing that process table.
So you cannot create complete processes.
Not using the shared memory OpenMP programming model. Okay, you do that using an MPI type programming model, which we will talk about maybe a month from now when we get to assignment 2. And this I'll repeat later on also. When these n-1 copies of the private variable are created, again, its user has to say something about how to initialize those copies. It's just that this is an address allocation. So user has control over, although there are some default behaviors defined, user has control over how those memory copies get initialized and how they get later collated. The
So previously you were saying in the shared case, they each will get a copy and this the mod specifies how they are collected.
That's for the private case. The shared case, there is a consistency model.
So it tells you how it collects, but here we have to specify how it has to be.
Yes. Yes. Okay. Now, they're also explicitly saying this is a private variable and this is a shared variable. There are also some things that are inferred. Okay. And in this slide, you see some restrictions on what must be inferred, what can be inferred, and what has to be specified. So anything that you allocate on heap can be shared. Okay. The static data members inside a function or inside whatever the variables that have been declared to be static are shared. Constant declared variables, const something, are shared. As long as sometimes you have a constant variable but that has members, so it may be a constant struct type with members that are mutable. So when I say that constant things must be shared, I mean constant things that are truly constant, that don't have any fields, any members that are non-constant. Anything that's declared inside as a local variable to a function, right? In this case, there is a parallel construct we are talking about. If it is inside the scope of that parallel construct, it is private. Okay, because it is essentially you are saying make copies of this. Everybody has a local copy of this. When you make a loop, what should happen? This is without saying anything. Sorry? It depends on what kind of loop, though, right? If there is a loop that is being shared by saying I am going to run from I equal to 0 to 3, you run from 4 to 7, this guy will run from 8 to 10, then you've got to have different copies of I. If you say, and in fact, this will make a little bit more sense when we talk about the actual construct details. There is a parallel construct and there is a loop construct. When inside a parallel construct, you write a loop. It says for I equal to 0 to 10, do something. And that I is shared. What will happen? I want to go from 0 to 1 and that guy is going at 3 to 4 and this other guy is doing something else. They all are running from 0 to 10, right? Because we are just forking off and everybody is doing the same thing. I also want to run from 0 to 10. He also runs from 0 to 10, but we are not at the same page. Right? We're not running at the same iteration level at any given time. And so we better maintain our own copies. Right? Also, question?
So what does the loop construct has to do with this? So the constraint that we are having is because of the parallel construct, right?
Whenever this loop is inside a parallel region, right? For some reason, multiple people are executing either this entire loop or a part of this loop. You need the variable that is being used as a loop iteration variable to be unique, right? To have it.
Even if there is we use the loop construct within the parallel construct, or we may not use the loop construct within the parallel construct. Since there is a parallel construct, the variables within have to be shared, private.
Yes, precisely.
So why are they treated separately, exclusively the loop construct? As in, I mean, could they not have been whatever the user is wanting to do?
Meaning you want the loop construct to be shared.
Yeah, I mean, if there is a possibility to define it in a private manner, then.
See, there are specified loop constructs, okay? And for that, the OpenMP is a pre-processing based scheme, right? So the compiler has to generate code by inferring certain things. So if you specify that is going to make that inference much harder. Although you can write non-loop construct codes, and then you can do shared variable and do whatever you want with it. And the arguments that are going to be get passed from function to function, if you pass a shared argument, then it's a shared. If you pass a private argument, then it's a private thing, right? All right, so this is about the consistency. And this, remember that this is in the context of having temporary views, temporary copies of variables, even when it is shared. This is not even talking about private. It says that if two threads write to the same shared variable and they're not synchronized with respect to each other, then after the two have written, I don't know what the value of the variable is. It will be one of those two, but I don't know which one. Okay, so it's undefined what the final result is going to be. And if the thread reads and another writes, again it's the same thing. It is unsynchronized. I don't know whether the read happened before the write or after the write. So what is being read is undefined. Okay, undefined doesn't mean junk. Undefined means I cannot precisely say what would have happened. Okay. And the amount that is going to get read from the shared memory, this is about, again, putting it in cache, is system dependent. Okay. If I read a struct, then different fields of that struct, different members of the struct, because the entire struct's read was not atomic, will have some from before that write, somebody else was writing that struct, and some fields, some members from after the write. Okay, so what is atomic? If the system says that you can write 16 bytes at a time. So if I have a struct that has 4 ints, then I'm going to be guaranteed that the entire read is atomic. So either I'm going to get all 4 ints from before the other write or after the other write. But if the atom size is 4 bytes, one integer, then I have no idea which of the fields come from before the update and which of the fields come from after the update. Okay.
So the model does not enforce any minimum atomic.
No.
It will differ.
I think that a byte is definitely supposed to be atomic, and I don't think even that is explicitly said in the specification. Okay.
It's the user unit to enforce that while we are coding.
It's system dependent, right? You will know which system you are working on, and you will know what its atom size is. It's not that atom size is supposed to be unknown to you. It is that atom size may differ from implementation to implementation. Okay, which means that if you have a Windows OpenMP, you may get a slightly different behavior versus running it on Linux. Okay, although it turns out that it's really determined by Intel, and so atom size in all these cases is 4 bytes. And there is this additional construct which makes the temporary view and the real view, the memory view of a variable consistent. Okay? So you can at any time say flush something. It's not the same flush that you may have seen in the C++ library. Right? It's not flushing something onto the file, into the disk. Okay? This is flushing to memory. So this is not that flush call. It is a construct flush. It will be inside hash pragma OMP flush. And in that flush, at one time, you can say, these are the variables I want to flush. And it is not necessarily a single variable flush. And we'll come back to it. This is something that needs to be understood properly because that tends to this is one place where you will typically find many bugs. And so now I'm reading from specs the actual definition of consistency. It says if the intersection of the flush set is things that are inside the flush directive. Say flush x, y, z. So that is a flush set. If the intersection of the flush sets of two flushes, which may be performed by different threads, are non-empty, right? So if some variable here also exists in that flush set, then their relative ordering is important. In specifically this fashion, the two flushes must be completed as if either this entire flush happened before the other one, or that entire flush happened before this one. Okay, you can't say A got flushed and the remaining things for that guy got flushed, and then this guy's remaining things got flushed, right? So the entire flush is atomic. And if it is empty, then doesn't matter which order you do them in. Okay, and the second, and that part is not listed here, although it's implicit, right? If two flush sets are empty, nothing is specified about it, which order they happen in. If you're talking about flush sets of a given program, their flush must happen in the order that they appear in that, sorry, not a given program, but in a given thread's execution order. That must appear in that thread's execution order. So if a thread says flush ABC and then flush XYZ, XYZ cannot be ordered before ABC. Okay. This is very similar to the consistency model that I had mentioned earlier. This is called the weak consistency model. The reason it is not exactly weak consistency model is that it is only among flush sets. The real weak consistency model says that any access anywhere has to be similarly ordered with respect to every other access. That is being abstracted out or moved at a higher level by saying that this is only going to apply to these special constructs that the user inserts wherever that is necessary. And it's only among those special flush constructs that this weak consistency model applies. Okay. So what that means is that this was not supposed to hide. But in any case, so this is showing you a flush sequence on a single variable. This is going to guarantee that something that was written in one variable is read by the other variable. It says that T1 is thread 1, is going to write to this variable. Then it is going to flush the variable, right? And because that is inside the same program, it has to be ordered. Right? Write happens, then flush happens. Now we are talking about T2. T2 is also going to flush this variable. And as long as that flush is ordered after this flush, any read after that flush from T2 will be able to read this variable. Okay. So this, if you want data from here to reach there, you're going to have to guarantee this. Now there are some times, if I probably will show you a couple, but you can look up the specs also. Some things are automatically flushed. From the context, it is given that you are requiring a flush. Other cases, you have to flush. For example, at the end of the parallel construct, everything is flushed. Everything that is in the shared clause. Okay.
So, what ensures that T1 flushes before T2 flushes?
No. Nothing ensures it. That's up to you.
How do we decide that sequential order? It's some sequential order.
That's user's problem, right? User has to ensure that whatever order is being desired is enforced. All this is saying is that this is the ordering that will ensure that T2 read happened after T1's write. Okay. How you enforce this order is up to you.
I mean, can you really enforce it if you do not guarantee this? I mean,
no, so you make sure that T1 flushes and then T2 flushes.
How do we enforce?
You enforce that by doing some lock, right? Mutex.
Again, right?
Sorry?
The lock is shared again.
No, so the lock may be shared, but lock has a separate consistency. Lock is by default flushed. Lock is one of those things. Otherwise, it wouldn't make any sense. You wouldn't call it a lock, right? Okay. So now let's look at one example of what I was talking about. I've got two threads. The thread on the left, it says thread 1. Thread on the right is thread 2. And in the beginning, some variable A and B are both, and these are shared variables, A and B are shared by them, are set to 0. Okay. And thread 1 says set B equal to 1, and which it is my indicator. When B is equal to 1, I'm indicating that I am doing something special. I'm going into the critical region. And now it checks if A is equal to 0, meaning the other guy hasn't set A to 1. Then go into the critical section, do whatever you want to do. After you come out, you probably will set B to 0. Similarly, the other fellow, which also wants to go into the same critical region, indicates that it is going to go into the critical region, checks that the other person is not in the critical region and goes in, if it is not. Okay, will it work? So my goal is that both of them shouldn't come into the critical region at the same time.
If the order is maintained, like B,
Which order?
like B is equal to 1, and then
If the critical section does not depend on B, then B equal to 1 may be scheduled after B in this whole loop.
That's the thing. So that's why the title says compiler can reorder your statements. Okay. So the compiler sees, oh, you're setting B equal to 1, but nobody is using it. This piece of code doesn't anywhere accesses B. So why do I bother setting it to 1? Doesn't set it to 1. Right? Maybe later on it uses B because something else is going to happen. It will reorder it. Right? So it can always go and move it here without any risk it might feel. Similarly, the other guy can also reorder A is equal to 1. And then there will be problem, right? Because I have not indicated that I'm going to go in the critical region, and I have gone into the critical region because when I came to A equal to 0, other fellow hadn't reached there yet. I go in, but I didn't tell anybody that I'm going in, and so the other guy just comes in and goes in. All right. What?
So why would the compiler do this if it knows it is a parallel code? Why would you want the compiler to do
So you want compiler to turn off all optimizations?
No, I mean, it's a possibility. As in, because you are sharing data, so B is a shared variable, right?
B is a shared variable. Yeah, B is being.
So you should not be optimizing for.
So shared variables shouldn't be reordered. You're saying that is a position you might take, right? But it is not the OpenMP's position, which means that if you don't specify any ordering, then the compiler is going to reorder, assuming that you don't need it. You know that it is a critical region, and you have decided that that's what means for me. That says that I am going in, which means you have to enforce that thing remains there. Okay, and that is why flush comes in. Now, if you say flush, again, unless the compiler knows something special about flush,
Otherwise,
it will just say these two together, right? B is equal to 1, flush B, both of them go there. It's the same problem. Okay. So how you would solve is using this flush set. If you make sure that flush AB is here and flush AB is there, then you know that these two are somehow related because they have common, they have an intersection that is non-empty. Right? So now these two flushes must be ordered with respect to each other, which in turn means that B equal to 1 must be ordered with respect to the second guy's flush. Okay. And so now you can figure out, while we take this break, why it should work or whether it should work. and then we'll start the next section after that. Okay.
Sir, like this intersection is non-zero, non-magnet between the flush set. So here, entire set 2 would run, then set 1 would come. I mean, you said that it becomes atomic mean.
Only the flush.
Means the data, the exception before the flush, but only the flush.
Only so the compiler doesn't say what has to be ordered. The compiler says that the system is going to guarantee that flush of A and B and that other flush of an A and B are ordered with respect to each other. There is a known relationship between these two flushes. Afterward, after the fact. When the flushes have happened, you know what that relationship is.
So you said
Actually,
that
flush is atomic with respect to the
Other flush. Yes. Yes.
So there is an order inside, but it doesn't matter, BA or AB.
Yeah. Order inside, it's just a set. It's not an ordered set.
Sir, it might happen that both the critical second don't run because.
Yes. This doesn't guarantee that. This is only ensuring that both cannot come in at the same time. It's if both of them think that the other guy is having it, they'll go through and probably try again.
So if you look at this, so B, then once at B equal to 1 and flushes, and then I'm not sure. I don't think what is why is that?
It says that the B equal to 1 has to happen before flush, right? And that flush has to happen either before that flush, right? Or after that flush. So you take those two cases. If it happens before that flush, then it's the way it was intended. If it happens after that flush, what does that mean? That means that A is equal to 1, because that flush happened before this flush, and A equal to 1 happened before that. And so when it comes here, A will be equal to 1.
So basically, A and B both can be 1 then sorry.
Yes. A and B both can be 1.
can we not put the condition that if B is equal to 1, then only you enter the critical section, so that you do not cause compiler reordering to happen?
You could do that, right? But it's better to simply use the mechanism that is provided, flush it, and that will happen. You can also enforce compiler reordering by using it. Yeah.
Ensure that compiler does not reorder.
Exactly. Okay.